Hello everyone, I am Matthieu Armando, a PhD student at Inria Joint Center, and I will present my ongoing work on Learn Multi-View Appearance Superresolution. This is a joint work with my supervisors Jean-Sebastien Franco and Edmond Boyer from Inria, and it is funded by Microsoft Research. The problem we are interested in is image-based modeling. Given some multiple observations of a scene as 2D images, we wish to compute a 3D representation of this scene that can be used to render novel views. More precisely, we're interested in the estimation of appearance information. So the first step is to reconstruct the geometry of the scene, and then we take as input 2D images and the reconstructed geometry in order to estimate a dense appearance information everywhere on the surface. This is a hard problem because of many sources of noise, and a common standard approach is to just follow a best view strategy, where for any point on the surface, a single view is selected to determine the color of that point. But that means discarding most of the available information. And well, because we have several observations of the same underlying information with different sampling, it should be possible in theory to perform super resolution, that is to compute a texture with higher resolution than that of any of the input images. So we perform a simple experiment. We implement a baseline texturing method with a best view strategy, and we compare it to some state-of-the-art methods. So G2Altec here is a more advanced best view strategy, and adversarial texture is a method where they train a texture to fool a discriminator when it is reprojected in the input images. So as expected, the state-of-the-art methods perform better than our baseline, but they are still lacking some high-frequency content. One naive way to extract high-frequency content from images is with so-called single-image super-resolution, which has seen a lot of interest recently, especially with CNNs. So a CNN is trained to enhance the resolution of a single image without additional context. So we can pre-process our low-resolution input views with a single-image super-resolution network, like ESRGAN here, for example, and then use the enhanced views as input for our baseline. And in our experiments, it turns out that this is better than the state-of-the-art methods run on low-resolution images, both numerically and visually. And this time we do get high-frequency content. So there are 2 points to be learned from this. One is that it's probably easier to enhance a signal in the signal space without transformation and resampling. So in our case, it's better to work in image space than in texture space. And CNNs are really good at learning priors on natural images. And a strong prior is a powerful tool. But still here, the high-frequency details are hallucinated, even though they are close to the truth most of the time. So we wish to combine the best of both worlds, that is to leverage a strong prior on natural images, like a single image super resolution network, but also use all available information. And there are existing works on Learn multi-frame super resolution, but they all work in a very limited setting with bursts of images from the same viewpoint. And in our case, we work with a wide baseline with occlusions, geometric noise, and varying input resolution. So very briefly, our architecture looks like this. So we take as input a view that we want to enhance and some additional images. And we extract high-frequency information from all views, and then they're all projected into the reference viewpoint. And the network aggregates them somehow and returns a RGB image in the end. So here are some results on our synthetic datasets compared to ESRGAN. The comparison is biased here, of course, because we have access to additional information, but it's a necessary validation step. And so we outperform them even on the most informative images. And here are some results on some real data. So here it's more challenging because the geometry suffers from noise plus specularities and missing surfaces. But still our method is quite robust, and we see here that for the single image super resolution network, some hallucinated content it does not match the real underlying color information. So that's pretty much it. Thank you for your attention, and I'm happy to take some questions.